Let me help you ace your Precalculus Exam 1 by solving problems from Unit 3 about polynomials and rational functions. In problem 1, we're going to graph some polynomial functions, clearly showing any x and y intercepts. Part A, the function is y equals x minus 1 quantity cubed plus 8. The key thing here is to recognize this as a transformation of a parent function. We can give this function a name. We can call it f of x. If we let g of x be just x cubed, we see that f of x can be found from g of x by replacing x with x minus 1 and then adding 8. Replacing x with x minus 1 takes the graph of g and translates it to the right by 1 unit. Adding 8 outside the function translates it upwards by 8 units. So if we know what the graph of g of x is, we can apply those transformations. The graph of g of x, the basic x cubed function, has this kind of shape like this, where you have what's called an inflection point at the origin, changing from concave down to concave up. Again, we translate this graph to the right by 1 unit and up by 8 units to get the basic graph of the function that we want, f of x equals x minus 1 quantity cubed plus 8. So if we mark 1 on the x-axis here and 8 on the y-axis, we have, again, this kind of shape is what needs to get graphed over here, about like this. But we are supposed to do more here. We need to clearly show what our y-intercept is right there and what our x-intercept is right there. The y-intercept is always easy. Just plug in x equals 0. What is f of 0? It would be 0 minus 1 cubed plus 8. That will be negative 1 cubed plus 8. Negative 1 cubed means you've got 3 factors of negative 1 being multiplied. Negative 1 times negative 1 times negative 1. 3 negatives, an odd number of negatives makes a negative. This is negative 1 plus 8. That is 7, and that makes sense. This should seem like it would be 7. What is the x-intercept right there? I drew it so that it looks like it's maybe negative 1. Is it really negative 1? Well, if you want to guess that it's negative 1, you certainly could just plug in negative 1 into the function here and see if you get 0 or not. In general, this is kind of guessing, and you may not be right. Let's see what happens. So we get negative 1 minus 1 quantity cubed plus 8. That's negative 2 quantity cubed plus 8. Negative 2 times negative 2 times negative 2 is indeed negative 8 plus 8 is 0. That confirms the x-intercept right here is negative 1. But what if you didn't know that? For the x-intercept, y is equal to 0. So we would want to solve for x by setting y equal to 0. If we do that, we get 0 equals x minus 1 cubed plus 8. This looks like it might be a difficult equation to solve, and in fact, if you expand it out into standard form, it would look really difficult. However, a little bit of trickery allows you to rewrite this as x minus 1 cubed equals negative 8. Essentially, I just subtracted 8 from both sides of this equation, and then I also switch sides. That's okay to do. Equality is symmetric. So x minus 1 cubed equals negative 8. Take the cube root, the real cube root of both sides. We'll get x minus 1. What's the real cube root of negative 8? It's negative 2, just like negative 2 cubed is negative 8. That means the real cube root of negative 8 is negative 2. Are there non-real cube roots of negative 8? There actually are. We will talk about complex numbers in this video as well, though we won't talk about complex roots in general. So we get this equation, x minus 1 equals negative 2. We add 1 to both sides, and we isolate x, and we get x is negative 2 plus 1. That is negative 1. That would be, in general, a better way to confirm that the x-intercept is negative 1 in this case. We were just lucky here in seeing that it really did turn out to be an x-intercept. In part B, we have this cubic. Y equals negative x cubed plus x squared plus 12x. If I had a constant term here, that would make this problem, especially the x-intercepts, harder. However, I don't have a constant term, and x can be factored out. That's a good thing to do right at the start here. Also, the leading coefficient is negative. Maybe we want to factor out a negative x to make it a little easier on ourselves here. However, you got to be careful what goes inside the parentheses after I factor out a negative x out of every single term here. Out of the first term, the negative sign is factored out. 1x is factored out, so I'm left with positive x squared. Out of the second term, I've got a plus x squared. I factor out a negative x. This has got to be a minus x, because if you checked by distributing this back through the parentheses, negative x times negative x is positive x squared. And then with the last term, I've got a minus 12. You can check negative x times negative 12 is positive 12x. Once I've done that, I see that I can factor this fairly easy. This one's not too bad. You also could use the quadratic formula, but a little bit of guesswork reveals that you can factor this as x minus 4 times x plus 3. You could double check this by foiling. X times x is x squared. Outside times outside is 3x. Inside times inside is negative 4x. 3x plus negative 4x is indeed negative x. And then last times last is negative 4 times 3 is negative 12. So now we see that the x-intercepts are going to be where this expression is 0. I want to set this equal to 0 to solve for x and the x-intercepts. When you've got a product of numbers equaling 0, that means one of the factors must be 0. So either x must be 0, or 4 to make that 0, or negative 3 to make that 0. These three numbers are x-intercepts. You can double check by plugging back into the original function. Again, y-intercept, that's always easy. That's just a function value at x equals 0. I could give this function a name, f of x. What is f of 0? Well, that's easy. And in fact, I know the x-intercept is 0, and x-intercept is 0, so therefore a y-intercept would also have to be 0. All right. Also, before I go ahead and make a graph without technology, I should think about the end behavior of a cubic. Now, if your cubic has a positive leading coefficient, the graph will either look like this or like that. And the end behavior will be to go to plus infinity as x goes to plus infinity, and minus infinity as x goes to minus infinity. But now I have a negative sign in front of that highest power. The leading coefficient is negative 1. That effectively flips the end behavior across the x-axis. So as x goes to plus infinity, y goes to minus infinity. And as x goes to minus infinity, y goes to plus infinity. The graph looks like this in the end behavior. And then again, I just got to get the x-intercept and y-intercept correct. X-intercepts at negative 3, 0, and 4, about like this. I know the graph has got to look at something about like that. That's going to be the general shape. It's got to go back up again in here. Something about like this has got to be what the graph looks like of this function. I'm not labeling the y-axis. Certainly I could do so if I use some technology, like this graphing calculator here. I could enter the function, say in its original form, negative x cubed plus x squared, and then plus 12x. Make sure my window is appropriate, like say negative 5 to 5 in the x direction. And what typically happens with polynomials like this, especially when they have a high degree, is they go up and down pretty rapidly. I'd probably want my y scale to be, say, fairly large, maybe negative 50 to 50 as an initial guess. With my tick marks 10 units apart, let's see what we see. There we go. Doesn't look too different from the graph that I drew on here. So effectively, this spot right about here would be about 50, and this spot right here would be about negative 50. In problem 2, we've got a cubic polynomial. P of x equals 2x cubed minus 7x squared plus 5. The directions first say to find the function value P of 3 using something called the Remainder Theorem. I'll remind you what the Remainder Theorem says as we go. Also, explain why this method works. So this problem is a little tough because we got to give an explanation. Before we use the Remainder Theorem, let's find the function value P of 3 by first using the ordinary method of substitution. Replace x with 3 everywhere you see an x. So I've got 2 times x cubed is 2 times 3 cubed, minus 7x squared is minus 7 times 3 squared, plus 5. Order of operations is essential here to getting this right. When you see the expression 2x cubed, that means do x cubed first and then multiply by 2. So we do 3 cubed is 27 times 2 is 54. We do not do 2 times 3 to get 6 and then cube that. That will give the wrong answer. You need to understand order of operations. powers before multiplication. In the second term, 3 squared is 9 times negative 7 is minus 63. And then we add 5. 54 minus 63 is negative 9. Negative 9 plus 5 is negative 4. Negative 4 is the answer to this, but we have not used the remainder theorem yet. The goal is to do that with the remainder theorem. How? What the remainder theorem says is that if you plug in a number, call it c in general, into a polynomial like this to find p of c, you can do that by dividing the polynomial by x minus c and finding the remainder. The remainder is the answer. That's a little confusing. We're going to divide, in this case, this function p of x by x minus 3. Not x plus 3, x minus 3. A linear function. We're going to get a constant remainder at the end. That remainder will be the answer. It should be negative 4 if I don't make a mistake. Divide x minus 3 into the polynomial 2x cubed minus 7x squared plus 5. I'm going to use polynomial long division. Then, since I'm dividing by a simple linear polynomial, I can also check this with synthetic division, which we will use a lot here, so I'll show you that method too. All right, so how do you do this? Go to the highest powers in both cases here. X there and 2x cubed there. Ask yourself, what do I have to multiply x by to get 2x cubed? I have to multiply it by 2x squared. Now do the multiplication of 2x squared times both terms here. Put the answer down here, then subtract, then repeat until you get a constant term at the end. 2x squared times x is 2x cubed. 2x squared times negative 3 is minus 6x squared. Subtract, you don't have to put a minus sign here, but I will. I'll also put parentheses to remind myself I have to distribute the minus sign through effectively. 2x cubed minus 2x cubed is 0x cubed. 0, I won't bother writing it. Negative 7x squared minus negative 6x squared is the same as negative 7x squared plus 6x squared, which is negative x squared. There's no linear term, so I subtract. I still don't get a linear term. 5 minus 0 is 5. So I get negative x squared plus 5. Now repeat. This is not a constant yet. I need to multiply x by negative x to get negative x squared. Put that negative x up here. This is going to be part of the quotient. Negative x times x is negative x squared. Put it down here. Negative x times negative 3 is plus 3x. I lined these up as if they were like terms, but they're not. Subtract. There's no linear term here. 0x minus 3x is negative 3x. The constant term is 5 there. There's no constant term here. Effectively, 5 minus 0 is 5. Still not a constant. I have to multiply x by negative 3 to get negative 3x. So I get a minus 3 up here. Negative 3 times x is negative 3x. Negative 3 times negative 3 is positive 9. Subtract. These cancel. I get 5 minus 9 is negative 4. Same answer as before. This is the right answer. That is the remainder I get when I divide the original polynomial by x minus 3. And again, the remainder theorem says that that remainder will be the function value at that number 3 in this case. Before we explain why this works, let's double check this with synthetic division instead. Synthetic division is similar to long division, but a bit quicker. It's when you divide by a simple linear polynomial like this, in this case x minus 3. The root of that is positive 3. It's the thing you're plugging into the function. Put a positive 3 here. Next, put the coefficients of the polynomial that you're trying to evaluate the function value at under here, including zeros for any missing terms. There's no linear term here. We're going to have a 0 for the coefficient of the x term. So I will write 2, first coefficient of the highest power, negative 7, then 0, then 5. Right? You do something similar here, except instead of subtracting, you add. It's another difference with synthetic division. And you don't have to write nearly as much. It's a quicker method. You start by bringing down the first number here, the 2, or effectively 2 plus 0 is 2. You don't see a 0 there. You could pretend there's a 0. Then you multiply. 3 times 2 is 6. Then you add negative 7 plus 6 is negative 1. Multiply 3 times negative 1 is negative 3. Add to get 0 plus negative 3 is negative 3. Multiply 3 times negative 3 is negative 9. Add 5 plus negative 9 is negative 4. That last number, same answer. It is the remainder that we get when we divide the original polynomial by x minus 3. You don't have to deal with the x's here either. Okay, just do it in this way. Do notice, however, as well, that the coefficients that I have here, 2, negative 1, negative 3, are indeed the coefficients of the quotient, 2, negative 1, and negative 3. But why does this work? In general, we've got a polynomial p of x, and we're dividing it by x minus c. And what we're claiming is that when we do that division and get a quotient and remainder, I'll call the quotient q of x, and remainder, in general, r of x, it could depend on x if we were dividing by a higher power of x here. But in this case, it'll be remainder, I'll call it capital R. What happens when you do that? By something called the division algorithm, which is not really an algorithm, but really a formula, a theorem, we can write p of x as q of x, the quotient, times x minus c plus the remainder. And again, in general, the remainder is a polynomial. But again, when you're dividing by a linear polynomial, it will be a constant remainder. What happens when you replace x with c on both sides here? Pretend c is a specific number, like in our case, x equals 3. P of c will be q of c times c minus c plus r. C minus c is 0. So this entire thing here is 0. I get 0 plus r is r. There we have it. The remainder that I get when I do the division is the same as the function value p of c. This is why it works. In problem 3, the directions are to graph this function, which you see is a quartic, a 4th degree. Oh, that doesn't sound so nice. And even do it without technology. You need to know some things to do this without technology, well at least. Showing clearly all x and y intercepts. Along the way, give a complete factorization of f. Evidently, it must be possible, not necessarily easy. Also, describe the end behavior of the function. I could describe the end behavior right away. It's a 4th degree, even degree, with leading coefficient that's positive. The end behavior is going to be like this. The function's going off to plus infinity in the y direction as x goes to plus or minus infinity in the horizontal direction. It's like a touchdown when that coefficient is positive. That'll be the end behavior. You could write f of x goes to plus infinity, goes up forever and ever, as x goes either to the right forever and ever or to the left forever and ever, as x goes to plus or minus infinity. That is the end behavior. We can say that right away. With the x and y intercepts, well, again, the y-intercept is the easiest one. That is the function value when x equals 0. We plug in 0. We get a bunch of zeros except for the plus 3 at the end. That is going to be 3. All right, the x-intercepts, that's the hard part. In finding the x-intercepts, that's also going to help us factor this function. To find the x-intercepts and completely factor it, we have to essentially be lucky. The teacher, me or your teacher, has to give you a polynomial that is relatively easy to factor with, say, ideally integer roots, or maybe a little less ideally rational roots. There's something called the rational roots theorem that says if you've got a rational root, the rational roots are of the form p over q, where p and q are integers, whole numbers, not dividing by 0 either. If you have a rational root, the numerator p has to divide the constant term, in this case 3, and the denominator q has to divide the leading coefficient, in this case 2. So the possibilities for p are plus or minus 1 and plus or minus 3. The possibilities for q, the denominator, are, again, the divisors of 2, plus or minus 1 and plus or minus 2. What are all the possibilities for the fractions that you can make from these numbers? When you divide by plus or minus 1, you get plus or minus 1 or plus or minus 3. And when you divide by plus or minus 2, plus or minus 1 divided by that will be plus or minus 1/2. Plus or minus 3 divided by that will be plus or minus 3/2. Plus or minus meaning one or the other, or possibly both. You've got ultimately 8 possible rational roots. Trying to do this without technology. Maybe we should try to guess what the graph looks like before we graph it most precisely. Again, the end behavior is certainly fairly easy. I can also think about the y-intercept. It's 3. All right, how else can I do this? I can think about the fact, this is a trick that maybe not everybody knows, the fact that the linear term has a coefficient of -5 means that the slope of the curve at this point is -5. More precisely, the slope of something called the tangent line there at that point is -5. The graph's going to go perhaps up or down, up, down, up. It looks like probably it's going to have a positive rational root, and in fact probably a couple positive rational roots. Maybe 1, maybe 1/2. Let's imagine plugging in 1. Okay, let's first start here. I'm going to get 2 plus 5 is 7. Minus 5 is 2. Minus 5 is -3. Plus 3 is 0. 1's going to work. You want to really confirm it? You could do it with synthetic division. I'm effectively dividing by x minus 1 by putting a positive 1 there. Put the coefficients of x, of the polynomial, in here. 2, 5, -5, -5, and 3. Make sure I didn't miss any. That looks good. Remember, if there's a missing term, to put a 0 down there with synthetic division. Bring the leading number down. 2, multiply, add, multiply, add. 1 times 2 is 2. Multiply, add, multiply, add. I got a 0 there. Yes, that confirms that 1 is a root. 1 is an x-intercept. Might wonder if it's a double root. That's a possibility. I could try plugging in 1 here. Let me just do it in my head, imagining these are the coefficients of a cubic. I get 2 plus 7 plus 2. That's up to 11. Minus 3 is 8, not 0. So 1 is not a double root. What's another positive root? The graph will come down and go back up again. There will be 2 positive real roots, but not necessarily rational. What's the other positive rational root? It could be 3, it could be 1/2, could be 3/2. Let's take some experimentation. Let me imagine doing 3 here without actually writing it. I bring down the 2. 2 times 3 is 6. 6 plus 7 is 13. 13 times 2 is 26. Yeah, 26 plus 22 is 28. Then I'll get a 56 here. It won't be 0. Looks like I better try 1/2 or 3/2. Let's try 1/2. Okay, let's just try it and see what happens. We might be wrong. I might need to redo it over here. Bring the 2 down. 2 times 1/2 is 1. Add, multiply, add, multiply. Yeah, that works. Oh, we got lucky. So 0 is the remainder when I divide this by x minus 1/2, meaning 1/2 is a root, a rational root. What I'm left with here now are the coefficients for a quadratic as I continue trying to find other roots. And the roots of that quadratic, 2x squared plus 8x plus 6, are going to be the other real roots. Are they rational? Can I factor this easy? Maybe I want to factor out a 2 first to help me. Yeah, I think I can. This factors as x plus 3 times x plus 1 in there. Double check it in your mind. That does work. That's going to mean -3 and -1 are a couple other rational roots. There are 4 rational roots here, 3 of which happen to be integers. -3, -1, positive 1/2, positive 1. The x-intercepts are those numbers, -3, -1, positive 1/2, positive 1. A complete factorization of f of x, well, that'll be one of the factors right here. I'll also have an x minus 1 and an x minus 1/2. I can factor f of x ultimately as 2x squared plus, well, okay, let's write the linear form of it. 2 times x plus 3 times x plus 1 times x minus 1 times x minus 1/2. That's one way to completely factor f. Another thing you could do is you could take this 2 and multiply it times any one of these factors. It kind of makes the most sense to multiply it by this one so the fraction goes away. So another way to factor this is as x plus 3 times x plus 1 times x minus 1 times 2x minus 1. I've got to multiply times each term. You do need to just multiply it by one of these here. If you multiplied it by all of them, you'll really be multiplying by 2 to the 4th, which is 16. Either one of these is a complete factorization of f, showing the roots are -3, -1, +1/2, and +1. As far as a graph goes, the final thing that we'll do, the roots are again at over here -1 and -3, and over here they are at +1/2 and +1. We knew the y-intercept again was 3. Trying to make this to scale, say, here in this window. So it's going to look something about like this. Okay, this is a little tricky here. I do know the slope here is -5. It's going to go up pretty rapidly like this before coming back down again. And do something about like this. It's kind of a weird looking graph, okay? Something about like that is what it's going to look like near the origin here. Let's try to confirm this with technology now. So change my function here. Plug in my original function here. 2x to the 4th plus 5x cubed minus 5x squared minus 5x, and then plus 3. Window, I want it to look about like what we see here, maybe go from -3.5 to +1.5. Y direction, maybe let's just try -6 to 6 and see if we get a picture that looks about like what we've got here. Maybe it goes up higher in here and goes outside the window. Let's see what happens. And it's going outside the window over here too as well. Yeah, the main issue of going outside the window is there. So I'd want to go down to say, oh, I don't know, -30 or something to see what we see. And now we do see that. We could also go to -20 instead, it looks like. We are basically getting it right here. Though it's subtle as far as how far it goes down here. You really do need the technology to see it. In problem 4, we have a quartic polynomial again. There it is. Part A says use Descartes' Rule of Signs, plus or minus, to determine how many positive and how many negative real roots the equation p of x equals 0 might have, counting multiplicities if it's a double or triple root, for example. What does Descartes' Rule of Signs say? It says that the number of positive real roots is equal to either the number of sign changes in the polynomial or less than that amount by an even number. Okay, how many sign changes are there in these coefficients? There's one from 2 to -17. There's a second from -17 to 53. There's a third from 53 to -72. And there's a fourth from -72 to 36. So the number of positive real number roots is either that number of sign changes 4 or smaller, less than it, by an even number, meaning either 2 or 0 as well. So we either have 4, 2, or 0 positive real roots, though this again does count or include multiple roots counted by their multiplicities. And that actually happens in this problem, we'll see. What about the number of negative real roots? For that, we need a little trick. We need to effectively reflect p of x across the vertical y-axis by replacing x with negative x. And if I do that, the even powers of x don't change sign in their coefficients because -1 to an even power is +1. And the odd powers do change sign because those are odd powers. -1 to an odd power is -1. So this is going to be 2x to the fourth plus 17x cubed plus 53x squared plus 72x plus 36. And there are 0 sign changes in those coefficients. Therefore, the number of negative real roots for the original polynomial, this one, is the same as the number of positive real roots for this one, which is 0. There are 0 negative real roots of the original polynomial. All right, next part B says, show that the number 9 is what's called an upper bound bigger than any other number that is a root of this polynomial. Also, 9 itself is not a root. Not. So what should we do here? We need to divide the polynomial, it turns out, by x minus 9. And when doing so, if we get a quotient that has all positive coefficients, and if the remainder itself is also positive, that will be enough to say that 9 is an upper bound of all the real roots. It's bigger than any real root of this polynomial. We can divide by x minus 9. We can also use synthetic division. Dividing 9 into this polynomial, x minus 9 into this polynomial. Put the coefficients down here. 2, -17, 53, -72, 36. There are no missing terms, so I don't put any zeros. So I'm hoping for all positive numbers down here. Bring the 2 down, that's positive. 9 times 2 is 18. -17 plus 18 is +1. +9, +62. Let's see, let's try to do that one in my head. 62 times 9, let's see, 10 times 62 would be 620. Subtract 62 from that, and we get what? 558, I believe. Maybe I better double check that. 9 times 62 is, yes, 558. Add -72, meaning subtract 72. Oops, 558 minus 72 is 486. Times 9 is a big positive number, 4,374. Add 36 to that. You're going to get 4410. The remainder theorem would say that's the function value at 9. But for us, it's important that all these numbers are positive. You could write it out in words now. This is enough to show that 9 is an upper bound for the real roots of p of x. In part C, we show that x equals 2 is a double root of p. In other words, a root of multiplicity 2. We can do more long division. We should get a remainder of 0 twice. And then the third time we do it, we should get a remainder that's not 0. So let's write down these same coefficients. 2, -17, 53, -72, 36. Bring down the 2. 2 times 2 is 4. -13, -26, +27, +54, -18, -36. Yay, 0. Okay, so it's at least a single root. Do it again with this part here. Should get another 0. 2 times 2 is 4, -9, -18, +9, +18, 0 again. Yay. But if I do it once more, I should not get a 0. 2 times 2 is 4, -5, -10, -1. Yeah, I did not get a 0. This is enough to say that x equals 2 is a double root. When we apply synthetic division, we got a 0 twice and not a third time. X minus 2 quantity squared will be a factor of p of x. All right, that proves it. Part D. Graph p of x, at least for x between 0 and 4. use technology to find all local extrema correct to 2 decimal places. Little hills and little valleys is what we're after. Not just their x coordinates, but their y coordinates as well. 2 being a double root means the graph of the function is just going to barely touch the x-axis, either like this or like that at x equals 2. It will not cross the x-axis there. It is a 4th degree polynomial with positive coefficient, and behavior is like a touchdown again, as before. And in fact, it's got a y-intercept of 36 and a slope of negative 72 at x equals 0. And no negative real roots. Yeah, that's why it makes sense to graph it for x positive. Something about like this. Will it just touch at 2 and then go back up? It could. What are the other real roots, if there are any? There is the quadratic that we get, the coefficients of it, when we divide p of x by x minus 2 quantity squared. 2x squared minus 9x plus 9 equals 0. What are the real roots of these? Let's see with the quadratic formula. We'll get a 9 plus or minus square root. Negative 9 squared is 81 minus 4 times 2 times 9 all over 2 times 2. Just using the quadratic formula. 4 times 2 times 9, that's 72. 81 minus 72 is 9. We've got 9 plus or minus square root of 9, which is nice, over 4. 9 plus or minus 3 over 4. The other 2 real roots are rational. 12 over 4 is 3. 6 over 4 is 3 halves, or 1.5. Okay, so that helps. Roots at 1.5, 2, and 3, about like this. Double root at 2. Okay, so it's got to cross there, and it's not a double root at 3 halves. Double root at 2, it's going to just touch there before coming back down again, and then this root's a little further away, so it'll probably come down further before going back up. Something about like that is the graph. Let's see if this is right. So again, go to my y equals screen. 2x to the 4th. Looking at the original function here, minus 17 x to the 3rd plus 53 x squared minus 72x plus 36. Window, x goes from 0 to 4. Y goes from, let's say, negative 1 up to at least, say, 50 maybe. Let's see what we got here. It's a little hard to tell what's going on here. If it really looks like what we drew there, I could zoom in closer. And in fact, we're ultimately going to need to do that to find the max. Let me make my window smaller in the y direction. Say 5 here and a 1 here. Redraw it and try to find the low points and the high points. Yeah, it just barely goes below the x-axis there. If I go to calculate minimum, for example, there is some minimum, not at 2, but a little to the left of 2, right about here. I can do a left bound for it, say right there, and a right bound for it, say right here, and a guess in here. There's a local min at about x equals 1.65 of approximately negative 0.05. You could write that down if you want. There's a local max, a little hill at x equals 2, and the y coordinate is 0. And a local min over here. Let's find that. Go back to calculate again. Tab over here. A left bound, say right here. A right bound over here. And a guess in here. Another local minimum at x equals 2.72 of value about negative 0.35. And that local minimum is also a global minimum. It is the lowest point on the graph. In number 5, our ultimate goal is to graph a rational function, a ratio of 2 polynomials, with the help of technology, but also by doing a bit of algebra, finding the quotient and remainder. With a rational function, a numerator and denominator polynomial, you really are doing a division. You can get a quotient and a remainder. We can do long division. We could also put a -2 here to help us do this division and get a quotient and remainder. The remainder is not necessarily 0. Again, put the coefficients, 1, -1, 1, -11 in this case. Bring down that 1, multiply, add, multiply, add, multiply, and add. -25 looks to be the remainder when I do the division. And these numbers are the coefficients of the quotient. The quotient is going to be a quadratic. We've got a cubic divided by a linear function. The quotient is going to be quadratic. Coefficients 1, -3, and 7. X squared minus 3x plus 7. That is the quotient. We've found those things. This is going to allow us to rewrite this function. We can take this information and bring it up here. We can rewrite this function as the quotient, this quadratic, x squared minus 3x plus 7, plus a new rational function where the numerator is the remainder, -25, and the denominator is the original denominator, x plus 2. Of course, we could also write this as x squared minus 3x plus 7 and bring the minus sign out front, minus 25 over x plus 2. What is this going to tell us? This is going to tell us, or help us even, graph it without technology if we wanted to. In the long run, as x goes to plus or minus infinity, as x gets big, positively or negatively, this is approximately 0 when x, or maybe let me say the absolute value of x, is large. How large is large? Well, it depends on the situation. You know, usually you could say 100 is large enough. So when x is large, this function is approximately equal to the quotient part, this quadratic here. So if we could graph this quadratic, it would help us graph the original function. Let me actually do that first. So let's go to my technology here, go back to my y equals screen. Let me graph the quadratic. X squared minus 3x and then plus 7. And let's see what that looks like. Pick a typical kind of window here, maybe -10 to 10. I'm going to go kind of wide. In the x direction, maybe -20 to 20, say. In the y direction, let's see what we see. There's the quadratic. Our rational function is going to have a graph that approaches this as x gets large. It will also have, as long as -2 is not a root of the numerator, which it's not because there's the remainder, going to have a vertical asymptote at -2. So our rational function is going to have a vertical asymptote right at this vertical line over here. Let's go ahead and graph the function to see all these things. Let's go back to y equals screen. Plug in the original function. I'm going to use parentheses. So I have x cubed minus x squared plus x minus 11, all divided by, in parentheses, x plus 2. Maybe we won't see a real great graph on this given window. Let's just see what we see. Should be a vertical intercept there, and you do see it getting close to this graph over here. What's happening over there? We don't see the graph. That's probably because it's way up high. And approaching this graph as x goes to minus infinity as well. Let's see, how could we see that here? Let's just go bigger in the y direction for sure, maybe -200 to +200. Make these tick marks 10 apart. Let's just see what we see here. Yeah, there's the graph of the quadratic. And oh yeah, you can see my rational function over here. It is approaching the quadratic as x goes to minus infinity and then going up at the vertical asymptote at x equals 2. Going like this in here. It does, I believe, have a positive real root somewhere in there. If we zoomed in closer, we could see it. I'm not going to bother drawing this by hand. The graph of the rational function, f of x, again, looks like this over here before going up. And then over here it goes up and then approaches the quadratic over here and has some x-intercept in there. In problem 6, we're graphing another rational function, this time without technology, and we're also describing its end behavior. You can do this without finding the quotient and remainder, though I think I will also find the quotient and remainder here. What's best to do in these kinds of situations, if you can, is to try to factor the top and the bottom, the numerator and denominator. In this case, we can. We can factor a 2 out of the top here, by the way, right away, like that. And what's left over, we can factor as x plus 3 times x minus 2. And the bottom can be factored as x minus 3 times x plus 3. And if your numerator and denominator in factored form have any common factors, you should cancel them out. That simplifies the function. Let me go ahead and maybe distribute the 2 back through the parentheses of here to get 2x minus 4 over x minus 3. These two functions are the same as long as x is not equal to negative 3, a root of what I divided out, x plus 3. This is if x is not equal to negative 3. The original function is not defined at negative 3. The new simplified function is defined at negative 3, but they can't be equal. Undefined can't be defined. What that's going to mean is ultimately we can graph this function by graphing this function, but putting a hole in our graph, so to speak, at x equals negative 3. There will not be a vertical asymptote there, it turns out. What is the end behavior of this function? The degree of the top and the bottom are the same in both cases, the original form and the simplified form. And also the ratio of the highest powers of x is the same, 2 over 1 and 2 over 1. 2. Y equals 2, a horizontal line at y equals 2 will be the horizontal asymptote for this function. And you could say, as far as describing the end behavior, y is going to approach 2 as x approaches plus or minus infinity. We will confirm this with division as well, but let's go ahead and just get a feel for what the graph looks like here before we confirm that. We are going to have a vertical intercept at, or excuse me, a vertical asymptote at x equals 3. We did not divide out an x minus 3. We'll also have an x-intercept at 2. All right, so let's get a little feel for what this graph looks like. There's an x-intercept there at 2. There's a vertical asymptote at x equals 3. A horizontal asymptote at y equals 2. We could also figure out, for example, the y-intercept, f of 0. It's going to be negative 12 over negative 9. That'll be positive 4/3 right about here. My guess is what this is going to look like is about like this. And there's also, don't forget, a hole in the graph at x equals negative 3, a point missing, so to speak, right around there. A missing point for the original function is what we're after, not the simplified function. And then over in here, I'm guessing it's above the horizontal asymptote over here. We could, for example, find f of 4 to approximate it. F of 4, 4 squared 16 times 2 is 32. 32 plus 8 minus 12 over 16 minus 9, it looks like. 40 minus 12 is 28 over 7. That is 4, if I did not make a mistake. F of 4 is 4, so the graph is up here, say. Probably going to look about like that. It's going to be what the picture looks like. And let's go ahead and do long division, say, of the original polynomial of the rational function, to see what that tells us, any extra confirmation. And if I am dividing by a quadratic, say I'm not doing this one, I do need to do long division instead of synthetic division. I will get a quotient that is just a constant term because the powers are the same. I need to multiply x squared by 2 to get 2x squared. It's just one step of long division here. 2 times x squared is 2x squared times negative 9 is negative 18. Subtract 2x comes down. Negative 12 minus negative 18 is negative 12 plus 18 is positive 6. And that is as far as I can go because now I have an expression whose degree is smaller than what I'm dividing by. So this is the remainder. And here is the quotient. It's a constant. This is the opposite of what's happened before where our remainders were constant. So what this means ultimately is the original function can be written in another form as the quotient 2 plus the remainder divided by what we originally divided by, x squared minus 9. As before, this part goes to 0 as x goes to plus or minus infinity because the degree of the bottom is greater than the degree of the top. And so the whole thing does approach 2. Y equals 2 is a horizontal asymptote as x goes to plus or minus infinity. Again, there's a hole in the graph. That's actually important in calculus. It's called a removable discontinuity, and they do arise in natural ways in calculus. I will add a little bit more to this function to say this function, because it's got a hole in the graph, it's a removable discontinuity that can be removed by just filling it in, so to speak. The function does have a limit as x approaches -3. It does approach a limiting value for y, whatever the second coordinate of this point is, as x gets closer and closer to -3 without actually equaling -3. If this is a new concept to you, don't worry about it too much. What is f of x approaching? I can use the simplified form of the function, which is equal to the function as long as x is not equal to -3, to help me evaluate this limit, 2x minus 4 over x minus 3. I can't use the original formula because I can't plug in -3. I'll be dividing by 0. But this function effectively fills in the hole at -3, and so I can evaluate this limit by plugging in -3. And I should get some number slightly less than 2, it looks like. So I get a -6 minus 4 over -6. -10 over -6 is positive 5/3. Yeah, 1.6 repeating is the y coordinate of the missing point on the original graph. If you're interested, this is pretty important in calculus. We've got two more big problems here, the last of which is a polynomial that has complex number roots. So in the second to last problem, we want to get a little bit of practice evaluating complex expressions and writing the answer in the form a plus bi, where I is the so-called imaginary unit, the square root of -1. It has the property that I squared equals -1. The imaginary unit. Does the imaginary unit exist? Yes, it does. Why? Because we define it to exist. It's not a philosophical problem. We define it to exist. The only issue is it useful? And magically, it does turn out to be useful. It's useful, for example, in differential equations, in electronics, and in quantum mechanics are some big uses of imaginary and complex numbers. It defines a consistent number system, having all the properties, algebraically speaking, that we would want it to have. It's beautiful. Here we want to get a little practice. Part A says evaluate I to the 15th. How in the world are we going to do that? We need to use this property and rules of exponents. In this case, it's essentially pattern recognition. If I squared is -1, then I cubed should be what? It should be I times I squared by properties of exponents, and that's going to be I times -1, so this should be -I. What about I to the 4th? That should be I times I cubed. I times -I. Negative I squared. But I squared is -1. This is +1. Isn't this fun? Whoa, amazing. I to the 5th, and by the way, that should also be I squared, quantity squared, and -1 squared is +1. I to the 5th will be I times I to the 4th. I times 1. I. We're back to I. I to the 6th will be I times I to the 5th. I squared. I times I. Back to -1. This is cycling. In fact, it's called a cyclic group. I to the 7th will be I times I to the 6th. I times -1, -I. I to the 8th will be I times I to the 7th. I times -I squared is back to +1, negative of -1, etc. Cool. Think about this. 15 is 3 more than a multiple of 4, just like 3 and 7 are 3 more than a multiple of 4. And in both cases, we got -I. Yeah, the pattern will continue. The answer here will be -I. Isn't that amazing? Okay, so that's right. That is what I to the 15th is. In part B, we're supposed to evaluate, simplify this fraction, this division really, into this form a plus bi. How in the world can we possibly do that? How can we divide these complex numbers? It's ultimately a little trick. We want to multiply this by something special, though the something special better be a disguised form of the number 1, otherwise it won't have the same value. To do that, it's analogous to rationalizing the denominator. But here we want to get rid of the, not the radical in the denominator, but the I. And the trick is to multiply the bottom there by 5 plus 2i. A new complex number with the same real part, so to speak, and the opposite imaginary part. I change the sign of the coefficient of the term involving the I. This minus changed to a plus. If this had been a plus, I change this to a minus. This is called the complex conjugate of this. If I do it to the bottom, I got to do it to the top, so that I'm really multiplying again by a disguised form of 1. And the magic here is that when I FOIL, and you can FOIL, on the bottom I'm going to get a real number. The outside and inside products will cancel. It's amazing. First times first is 25. Outside times outside is 5 times 2i is plus 10i. Inside times inside is 5 times negative 2i is minus 10i. Yeah, those cancel. What about the I squared? Last times last is minus 4i squared. Well, the I will go away there because anytime I see an I squared, I can replace it with negative 1. Do the same to the top, but the i's will not go away in the top. That's okay. 4 times 5 is 20. Outside times outside is 4 times 2i is plus 8i. Inside times inside is minus 15i. Last times last is going to be minus 6i squared. Replace that I squared with negative 1 as well. Combine the like terms. In the top I get 20. Minus 6 times negative 1 is plus 6 is 26. Negative 6 times negative 1 is positive 6. 8i minus 15i is minus 7i. On the bottom I got 25. Negative 4 times negative 1 is positive 4. 25 plus 4 is 29. To write it in this form, I should also split this apart like this. 26 29ths minus 7 29ths I. That will fit this form where A is 26 29ths and B is negative 7 29ths. That is the answer. Okay? You could check this, by the way, by taking that expression, multiplying by 5 minus 2i, and seeing that it will simplify to 4 minus 3i. This does work. Part C, we are expanding this binomial in I, this expression a plus bi, to the 4th power. You could do it as 2 minus I squared and then simplify that and square it again. You also can use Pascal's triangle even with this situation. Let's do it that way. So these are going to be the coefficients when I expand this binomial involving I. Oops, that's going to be a 6 there. All right, this is pretty tricky. What do? We've got to focus on this row here because it's a 4th power. This first number is going to be the leading coefficient of the first expression, 2 raised to the 4th power, times the second expression, negative I, raised to the 0 power. Yes, that will still be a 1. Anything to the 0 power is 1 except 0 to the 0. Then the next term is going to have 4 as its leading coefficient, times the first expression to 1 lower power, the 3rd power, times the second expression, negative I, to 1 higher power. Keep going. The next coefficient is 6, so I get plus 6 times 2 squared times negative I squared. Then the next coefficient is 4 times 2 to the first times negative I to the 3rd. Last coefficient is 1 times 2 to the 0 times negative I to the 4th. Since I got a bunch of negative i's to these powers, I probably should figure out what those are. This is certainly a 1. This is certainly negative I to the first power is negative I. Negative I squared, think about that. That's the same as negative 1 squared times I squared is positive 1 times negative 1 is negative 1. I squared is negative 1. Negative I squared is negative 1. Negative I cubed, that's negative 1 cubed times I cubed. Negative 1 cubed is negative 1. I cubed, we saw that before, that was negative I. So I get negative 1 times negative I. This is a positive I. And negative I to the fourth turns out to be 1. You can check. All right, so we're almost done. Simplify. We got 1 times 2 to the fourth is 16 times 1 is 16. Here, this minus sign can come out in front. 2 cubed is 8 times 4 is 32, minus 32i. Here we've got 2 squared is 4 times 6 is 24, times negative 1 is negative 24. 8, 4 times 2, times I is plus 8i, and then 1 times 1 times 1 is 1. Combined like terms, the real parts without the i's are these things. 16 minus 24 is negative 8, plus 1 is negative 7. And the I parts are these ones. Negative 32i plus 8i is minus 24i. So there is our answer. We're finally to the last problem. Congratulations if you stayed with me here. Find all rational, irrational, maybe real numbers that are not rational, like square root of 2, yeah, and complex roots, state their multiplicities for this fourth degree quartic polynomial. Use whatever techniques seem helpful, like technology. Then factor this polynomial. Yikes. One thing I notice is that every term is divisible by 6. I can factor out a 6. That could be nice here. 6 times in parentheses x to the fourth minus 3x cubed plus x squared minus 5x plus 6. So now let's focus on this thing right here. Let's jump in right away with the technology here. Clear this out. Go to my y equals screen. Clear these out like that. All right, we're trying to graph. Let's go ahead and just graph the part without the 6. I'll just leave the 6 out in front. It'll be a vertical stretch of this graph that I'm about to graph here. X to the fourth minus 3x cubed plus x squared minus 5x plus 6. The y-intercept of that thing will be 6. Who can say offhand what the x-intercepts will be? I'll go ahead and try this window to start with and then narrow it down a bit. It is a fourth degree. Okay, I'm going to want to zoom in there closer, like negative 4 to 4 maybe, and negative 25 to positive 25. Let's see what we see. All right, looks like perhaps 1 is a root and perhaps 3 is a root. Let's hope so. Let's try 1 as a root. I could just plug in 1 right away. I guess I could do that in my mind, but although it'll be good to do synthetic division anyway to help us divide and ultimately factor this thing. So let's go ahead and do the synthetic division like this. One more time, or maybe a couple more times. 1, multiply, add, multiply, add, multiply, add, multiply, add. Yeah, I got a 0. Yay. We're always happy when that happens here, when we think that's a root. So 1 is a root. I thought 3 might be a root as well. Let's try the 3. Bring down the 1, multiply, add, multiply, add, multiply, add. Yep, got a 0 again. What's left are going to be the coefficients of quadratic that'll have the same roots. X squared plus x plus 2, set that equal to 0 and solve for x. Are those going to be irrational numbers or maybe complex numbers? Negative 1 plus or minus square root of 1 minus 4 times 1 times 2 is minus 8. Yeah, we're going to get complex roots over 2 times 1. Negative 1 plus or minus square root of negative 7 over 2. Negative 7 can be thought of as negative 1 times 7. And that square root can be separated like this. And I have the square root of negative 1. That gets replaced by I. So I got negative 1 plus or minus I times square root of 7 over 2. Yikes. Complex numbers involving irrational numbers. Negative 1/2 plus or minus square root of 7 over 2 times I would be another way to write this. What is square root of 7 anyway? It's a number between 2 and 3. It's approximately 2.64575. I could write this as negative 0.5 plus or minus 2.64575I in approximate form. So we found the roots, 2 real roots that are also rational, 1 and 3. 2 complex roots, these two numbers, negative 1/2 plus square root of 7 over 2i and negative 1/2 minus square root of 7 over 2i. They're complex numbers. They also involve an irrational number, square root of 7, though you wouldn't call them irrational because they're not real. They all have multiplicity 1. As far as factoring the polynomial then, if I want to make sure to include the 6 out front, I can write it as 6 times in parentheses x minus 1 times x minus 3. And yeah, I could write it as x squared plus x plus 2, but if we want to completely factor this with linear polynomials, I'd want to write x minus in parentheses negative 1/2 plus square root of 7 over 2i, and then finally x minus negative 1/2, almost out of paper, minus square root of 7 over 2i. That's a 7 there. Yikes, that is a complete linear factorization, a splitting, so to speak, of this original 4th degree quadratic. It's emphasizing there are 4 roots, the same as the degree, all of multiplicity 1. You add up the multiplicities of all the roots 4, you get the degree of the polynomial. This is a confirmation of what's called the Fundamental Theorem of Algebra in this context. Any polynomial, no matter what the coefficients are, even if the coefficients are complex numbers, amazingly, will have complex roots. And in fact, if you add up all the multiplicities of the complex roots, it will equal the degree of the polynomial. You can think of real numbers, by the way, as being complex numbers. 1, for example, could be thought of as 1 plus 0i. So I wasn't misstating the theorem. Also, do note that these 2 complex roots are complex conjugates of each other, same real part and opposite imaginary parts. That will always happen, it turns out, if your polynomial has real coefficients, though it doesn't necessarily happen if they have complex coefficients. Final thing to do is you can graph these roots in what's called the complex plane, where you label the axes with the words real and imaginary. But that imaginary axis is there, I drew it. It's there. 1 and 3 are roots. And these 2 complex numbers, here again are their approximate values. Going to be right around, say, here and here are roots. They're complex conjugates. They are reflections of each other across the horizontal real axis. And again, that will always happen. They will come in complex conjugate pairs when your polynomial has real coefficients. Thanks for watching.